Hello and welcome back. I haven't recorded a video in a while, but I thought it would be fun to look at my all-time favorite Advent of Code problem. This is 2019, day 14, space stoichiometry. I think that's how it's pronounced. I've recorded a video on this before, but that was several years ago, and I've learned some more as an APL programmer. I have a couple additional tricks that I can use. And this is my favorite problem because, well, A, I think the problem is very interesting, well put together, and B, there's a great array-based solution. That's not it's not evident if you look at it, but I think everything flows together sort of nicely. So let's take a look. All right, 2019, day 14. The idea is that we have this list of reactions. So we get a text file, each line denotes a reaction, and the output is on the right, and the input is to the left of this arrow here. And so we have one reaction that produces fuel, and we also have a number of reactions that take ore as input. So you can think of fuel as the thing that we ultimately want to produce, and ore is sort of the base cost of everything else. And we're trying to figure out how much ore we need to spend in order to produce 1 unit of fuel. So you can see with these reactions, they're kind of, they're nested, or they reference each other. So in order to produce 1 fuel, we need to produce 1 E component and 7 A components. And of course, there's a reaction for E and there's a reaction for A. Now, the important thing about this problem, and the thing that sort of gets a lot of people tripped up, I think, is that the reactions can produce a number of units that doesn't exactly divide with what you need. So let's say that we had to make this C component here. We need 7 A components, but we only have a reaction that produces 10 A components. So we have to run the reaction once, and we use the 7 A components that it produces, but then we have 3 left over. And, importantly, we can use those 3 leftover A components to serve as a surplus that we can use in future reactions. So you need some sort of good way to account for that. Anywho, so this is just an example that goes through, different recipes and stuff. And yeah, basically the question is, what is the minimum amount of ore needed to produce exactly 1 fuel? Fair enough. All right, so, and bear with me because I'm doing this on a Mac for the first time. You may not know this, but Dyalog works pretty well on Mac OS, and I have a new keyboard. So I may not type as fast as I usually do, but let's see. So we are getting 14.txt, and that's our input. Now, basically, if you look at this, the only pieces of information that we really care about are the numeric values and the alphabetical values. So these things like spaces, commas, the arrow itself, it doesn't really matter. And the reason the arrow itself doesn't really matter is because we can just say, the last item in this list is always going to be the output. So that's enough to designate it. Now, I've done in previous videos, I've done this sort of extraction where you can do quad D, membership, commute, partition, right tack, something like this. And that's sufficient to get all of the digits out. And if I do quad A here, that's enough to get all of the letters out. But if we want to get both of them, we can we can do that more efficiently with an outer product. So this will be membership, partition, left tack, and then we commute here. And this gives us a 2-column matrix where on the left column for each row is the the numeric values associated with the row. So these would be the amount of inputs and outputs. And then the right column, we have our list of designations, or you can think of them as like ingredient names or reaction names. Okay, great. And what I'm going to do is for each one of these columns, or each one of these cells in the matrix, I'm going to reverse the order. And the reason why I'm doing that is because remember, I was saying in the raw input, the last value is sort of special because it's the output. If we reverse everything and we make the output be the first value, it makes it a little bit easier to work with later on. So we will assign this to P, and one of the first things that we're going to want to do is get a unique list of all of our ingredients or reactions. So if we take the rightmost column of P, and then for each one of those, we take the first value, we get a list of all of the outputs from the reaction. The trick is that we have one more component that doesn't have a reaction associated with it, and that is OR, and we can just put that in the first position here. And we can assign this list to I for ingredients. Now, what I want to do next, and this is sort of core to how we think about the problem, I'd like our data structure to be a matrix where each one of the columns designates one of our components here or ingredients, and then each row will be a particular reaction. And I want the numbers in each row to correspond with the number of components required for input and the number of components required for output. And I think if we put everything into a matrix this way, we can come up with a cool algorithm that will allow us to solve this problem in like a particularly array-based way. So if I look at my problem input, this is our two-column matrix, I can run a reduction on it. And if I reduce, that's for each row, I'm basically inserting this function that I'm building on the left between the two values in the row. So the numbers of each components will be on the left, or alpha in this function that I'm building, and the actual identifiers will be on the right, or they'll be omega. Okay, so if I'm building a row in a matrix, it makes sense to just sort of build an empty row first. So we can say 0 constant for each ingredient, and that builds this. If we mix it together, we get a matrix full of zeros. That's a great start. And then essentially at the indices indicated by the identifiers, I want to insert some numbers. So we'll say at ingredients index of omega, and remember that omega is our right-hand argument and contains all of the identifiers. Now we have to actually pick some numbers to go in there, and that'll come from alpha on our left-hand side. So first we have to do a for each execute on alpha because they're still strings at this stage. We haven't turned them into numbers. And then remember when I said that the output is special, and so since we did the reverse, the output is now the first element of each one of these lists. So we can do at 1, at the very first element, we're going to negate. And basically what this is saying is that within each row in the matrix, the positive numbers are going to denote the inputs to the particular reaction, and there will be a single negative number that designates the amount of outputs that the reaction produces. This is sort of arbitrary. You could just as easily make the outputs positive and the inputs negative. The important thing is that we just have a way to differentiate the two. So if I run this reduction, I get this, and then if I mix it, I get an interesting matrix where across the almost diagonal here, we get a bunch of negative numbers that denote the outputs the number of outputs for each reaction, and then we'll have a bunch of positive numbers in each row that denotes the number of inputs required. So now the trick with this is if we look at the shape of this matrix, it's 63 by 64. And the reason it's not a square matrix is because we built this off of our input here, which contains all of our reactions. And remember that we don't have a reaction for OR. And I think that we can represent OR by just putting zeros along the top of this matrix. So now if I do like I catenate, you can see that so each row represents a particular reaction. For OR, because there's no reaction, we basically have no output, no inputs, so everything's just zero. And then for every other reaction, we have a single negative number that denotes output and some positive numbers where their indices here represent the ingredient that they're taking as input, right? Okay, so with this matrix complete, we can call this M. All right. Now, our problem asks us to figure out how much ore we need for a particular unit of fuel. So presumably the very first reaction that we're going to want to run is the fuel reaction. We can find that by doing ingredients index of, in close, fuel. That gives us 48, which we can then index into our matrix to get the particular row associated with the fuel reaction. So yeah, it looks like it takes 12, 28, 15, et cetera, et cetera. And we should have a -1 here, which denotes that this reaction produces exactly 1 fuel. And then we can run a function on this. So, excuse me. You can think that basically, so we know we have a bunch of positive numbers here, which denote components that we need to produce. And we have reactions that can produce those components. Each reaction has a set amount that it outputs. So imagine that we needed 16 components, and we have a reaction that produces 5 of that component. Well, we would need to run the reaction 4 times, producing 20 total components, and we'll use the 16, and then we'll have 4 as surplus, right? Basically, we can't run partial reactions. It's all or nothing. So the way that we determine how many times we have to run the reaction is basically the requirements divided by the amount that's produced in the reaction. So in our example, if we need 16 components and we have a reaction that produces 5, we can do, sorry, I don't know what this is offhand. We can do 16 divided by 5, we get 3.2. And because we can't run partial reactions, we'll want to round this up to the nearest whole number. So we can say that we need to run it a total of 4 times. Now, we have this complete row that tells us what all our requirements are. If we do a min scan or a min reduce on our matrix, so we're reducing across the rows, taking the minimum value basically pulls out all of the negative numbers, which remember that the negative numbers equate to the amount that the reaction outputs. So min reduce gets us the negative numbers, or in other words, gets us the amount that each reaction outputs. And then if we negate that, we get like sort of the absolute value, or the amount of things that the reaction produces without this sort of arbitrary designation of being negative. So when we, let's see, so we have our fuel row and we're running a function on it. One of the first things, oh, no, you don't have to go all the way over there. One of the first things that we can do is we can do a min reduce on M and negate, and that gives us this. And we'll want to take our input and divide by all of the outputs, so we get the number of times that we have to run each reaction. But we have to do a little processing of the input first. So I'll just take the error here. If we look at ingredients, we can see that the first ingredient that we have here is ore. And what that means is that as we, if we look at if we look at our input into the function that we're building, the very first value will be the amount of ore that's required. And this will be a positive number because it's a requirement. But the thing is that we don't actually want to run the OR reaction because there is no such reaction. So what we can do in terms of just kind of pre-processing our input here is we can do a 1 drop omega and then conza 0 onto it. And this is basically just saying like whatever the positive OR value is, just get rid of it and replace it with a 0. So we're almost like excluding it from consideration here. And if we do this, all of the sort of non-zero numbers here are the number of components required divided by the number of components that each reaction produces. And we get fractional numbers here. And weirdly enough, we get 1 in the leading space, seemingly indicating that we have to run the OR reaction. And that's simply because Dyalog is nice enough when we do 0 divided by 0, rather than giving us a divide by 0 error, it gives us a 1. So, anywho, so in this case, remember that we can't run fractional. Oh, we have to do one other thing, by the way, which is that we have to do 0 max on our input, because we are only interested in the requirements that we need to figure out the reactions. The outputs, or our surplus, if you want to think of it like that, they're all represented by negative numbers. And so when we're figuring out how many times we want to run reactions, we just want to 0 those out so that they're not part of the consideration. And then because we can't run fractional reactions, we'll do a ceiling here. Oh, nope. That has to happen after the division. We'll do a ceiling here to round everything up to the nearest whole number. Okay, so this vector here now sort of tells us how many times we have to run each reaction. And the length of this is 64, and the shape of our matrix is 64 by 64. So what would be really cool is the way to solve this would be to take this row that we've calculated, and for each number here, we want to multiply by the corresponding row in the matrix, right? So if we want to run a reaction 12 times, that's sort of equivalent to multiplying all of the inputs and the output of the matrix by 12. And then once we've done all that multiplication, we add everything together, and that's going to tell us, that'll give us our surplus, or the things that we're producing, and it will also give us a set of new requirements denoted by positive numbers from all the reactions that we're running. And the really interesting thing is that you can do that with an inner product. So if we do in plus dot times commute, we get this. Now, inner product took me, to be honest, probably like a couple years to understand properly. But essentially what it means in this case is we are taking a vector, and for every column in our matrix, we're sort of laying the vector over it and doing a multiplication, and we repeat that for every column. And then at the end, we add everything up, or we do a plus reduce. And that's equivalent to multiplying every row in our matrix by every number in our in the input that we've calculated. Then we add everything up. And as you can see, we get a number of outputs denoted by negative numbers, and we get a number of inputs now divided by positive numbers that we're going to have to satisfy. The final step here is to add this to our original input to the function so that we can say, hey, we ran the reactions, we produced these things, now we need to add them to our current set of surplus and requirements. And that gives us a new value here. And yeah, this is sort of a complete iteration of running the reactions that we need to run. We can see that we still have a bunch of positive numbers here, which means that we need to run more reactions. And we could use the power operator here to say run this, twice. We can run it 5 times. We still see some positive numbers here. What if we run it 100 times? Oh, now this is interesting. So, our first number here, the amount of ore that's required, is still there, but everything else is either 0 or a negative number. And when it gets to this point, this 0 max that we're doing on our input is essentially going to zero everything out. And the 0 vector inner product with our matrix is going to also result in a 0 vector. So, and then when we add it to the input that came in, then it's just going to be the same value again. So watch. So we ran this 100 times. If we run it 101, we run it 105 times. If we run this 200 times, it's still the same thing. So what we can actually do here is we can just do a power match, or basically run the function until it converges and the output doesn't change anymore. I've done this a lot in my previous videos. And now, in order to get the amount of ore, we can just take the very first value. And that's 114, 125, which looks like that is the answer for part 1 anyway. Okay, hopefully this makes sense. So basically we have this big matrix. This is sort of the core insight here. We have this cool data structure, and we basically do matrix multiplication on a vector containing all of our requirements and surpluses in order to run the reactions. And we keep running those reactions until there are no more requirements, at which point we can pull out the total number of ore that we've sort of built up over the course of running all these reactions. Whew, all right, so that's part 1. Now part 2 is sort of interesting. Part 2 says, after collecting ore for a while, you check your cargo hold and it turns out that you have 1 trillion units of ore. This is equivalent to 1 E12, by the way. And the question is, given 1 trillion ore, what is the maximum amount of fuel that you can produce? And now we sort of have this problem because we have a function that tells you the amount of ore that it costs to, well, actually, no, we don't have a function yet. Sorry. Let's build a function. So let's say that we have a function f, and we'll just wrap this whole thing, and the only difference that we really have to make is we take omega times our fuel row. Basically, again, when we're running a reaction multiple times, you can just use multiplication. So because this fuel row produces exactly 1 fuel, if you want to produce 10 fuel, we just multiply everything by 10, both the inputs and the outputs. So that's our function f. And if we run f on 1, we get our part 1 answer. But we can just as easily, do larger numbers, and this will tell us how much ore is required to produce that amount of fuel. But now we sort of have to work backwards, and we have to say, given a set amount of ore, what's the maximum amount of fuel that we can produce? The answer for this is sort of mysterious, and I think, It's kind of mysterious, all right. I'm just going to type the answer first, and then we can explain how it works. Okay, so this is min right tack times 1e12 divided by f power match 1. And that gives us 120, 39, 407, which is indeed the answer for part 2. All right, so what on earth is going on here? The core insight is that essentially each time that you produce more fuel, you're more efficient in terms of ore because you're able to use the surplus. So if I had to produce 100 ore, if I, let's see. So here was our output of all of the surpluses and the ore for producing one fuel. You can see that we have a ton of negative numbers here, which denote like a ton of surplus that's being just left on the ground after we're done producing our fuel. So if you had to produce 10 fuel, if you produce them one at a time, then all the surplus is going to waste. However, if you produce the 10 fuel all at once, you're able to use that surplus, and that brings your ore cost per fuel down. So I can sort of demonstrate this if I do like iota 9, 0 cons. We can do like 10 to the power each time. We can do for each. Do f, and then right tack divided by, I think, not the other way around. Divided by right tack, yep. And then let's actually move this here, and then we can do right tack shots dot like so. Okay, so this tells you the ore cost to produce a single unit of fuel as you move up and you start producing more fuel at a time. So if we're just running the reaction and we're producing one fuel, it costs us, 114,000 ore to do. If we're running the reaction and we're producing 10 fuel at once, however, the total amount of ore required for each unit of fuel goes down significantly. And you can sort of tell just by looking at this that as you produce more and more fuel at once, your average cost of ore per unit of fuel continually goes down. And it looks like it sort of converges at this 83,060 number, right? Okay. So one way that we could think about this is basically we have the amount of ore that it takes to produce 1 unit of fuel. What if we do 1e12 divided by this? That tells us, basically you could expect to make at least this much fuel. You could expect to make at least this much fuel with the amount of ore that you're putting into each unit of fuel with that amount. So if I do, if I do this, and then if we do like right tack times, this is just basically saying like, if I run, if I'm producing 2 units of fuel, then F is going to give me the cost to produce a block of 2 units of fuel. I'm dividing that amount by 1e12, and if I do 2 times that amount, then it will get me sort of the base amount of fuel, right? This is sort of how you convert from having a reaction that produces multiple amounts of fuel to getting your individual fuel units. And then I do a min here because according to the problem description, we want to produce the maximum amount of fuel we can up to 1e12. So if we do a minimum here, it cuts off any fractional values and keeps us from exceeding that 1E12 value. Okay, so if I do this once, this is basically telling me like, oh, sorry, I meant to run it on 1. If I do this once, this is basically telling me that if I run the fuel reaction one at a time, I can expect to get, 8,760,000 units of fuel from 1 trillion ore. But if I run this on that number, now I'm producing all of this fuel at once. And so it's basically saying like, yo, given the sort of more efficient ore cost, now you can expect to produce this much fuel. You see that it's larger than before. And if I run it on this, now the value doesn't change. So now for 1 trillion ore, we've pretty much reached maximum efficiency. And so we can just do this on power each, and that gives us our part 2 answer. So hopefully that makes sense. The basic idea is that as you produce more fuel at once, your ore efficiency goes up, and you can, sort of figure out how much fuel you can produce, for a given amount of fuel that you're running at once. That sort of serves as a lower bound, and then you can, keep trying to raise that until you hit the 1E12 ceiling. Okay, let's put this all together. So I'll do like 14 video.dialog. Yep. Okay, all the way back here. So let's see, this is our input, and then we had some ingredients. Actually, yeah, I could put that on a separate line, but let's do it as part of one line for right now. It looks a bit worse with the size of the font. Okay. So we'll cut this. So that's our ingredients. And then we build our matrix, and that's here. And then we have our big function, and that's here. And then we run f on 1, and that's part 1. And then our part 2 solution is here. And that is part 2. Okay. And so if I copy this whole thing, yes, we get the correct answers. Okay, now, this solution in and of itself is already pretty nice. It's concise, it uses like large arrays, it's pretty array-based, it seems well suited to APL, but the really cool thing about it is that it performs really well. So let's pull compex from defense. And if I do compex on F1, this is just calculating, how much ore a single unit of fuel takes. 2.4 E5, what is this? I think this is 24 microseconds. Not milliseconds, microseconds. And if we run our part 2, this is the cost here is basically we're running our f function, 2 or 3 times? Yeah, so it comes back at 83 microseconds. So, I mean, it's pretty wild that, you can do all those, you can do all those calculations so quickly. Let's see, if I was going to do the whole thing, including the parsing and building the matrix and everything, we can build a function g like so, and pull this stuff in. And this is now, we can assign this to P1. We can assign this to P2. And I'm going to take disk access out of the equation. So we'll do like this. Okay. And then if I say like txt is equal to and give 14.txt1, that's our input. And if I do g on txt, oh, interesting. Oh, yes, right. I do need to output these values. Yeah, I get the correct answers. And if I do compx g on txt, this now gives me about 670 microseconds. So we're still lower than a millisecond, but it seems like we're wasting a lot of time just building the matrix. There are some improvements that we can do here. For instance, we could keep I in like a hash table like this, and then we can use it in locations where we're performing these lookups. So it'll be there and here. What else? Oh, this min scan doesn't change between iterations. So, you know, we could call this like Z, like this. Replace this with Z. I think honestly that gets you like most of the way there. Oh, and we're also doing a lookup for the fuel row, which we don't need to do in sort of the tight loop there. So we can call this R. Yeah, and I think, so that's G. We still get the correct values for G. But now if we do compx G txt, I would expect this to be a bit faster. Yes, we lose about 120 microseconds, and now we're down to 550 microseconds to run the entire problem. So it's like half a millisecond. So anywho, yeah, without the performance improvements, the code looks like this. I think it's pretty cool. It's a very neat array-based solution. It's performant. The problem itself is interesting, and that is why this is my all-time favorite Advent of Code problem. So yeah, I know it's a bit out of season, but I hope that you've enjoyed watching this. Let me know what you think. All right, thank you.